Okay, in this video we're going to take a look at dot products. We're going to introduce dot product here. We're going to start by finding the dot product of two vectors and describe what that is. So if we have two vectors v and w, where v and w have horizontal components and vertical components, so horizontal component of v is v1, vertical component of vector v is v2, etc. for w. The dot product of v and w is, it's almost like a way to multiply vectors. Use that term very loosely, multiply vectors, but essentially v dot w, we take and we multiply the horizontal components, so v1 times w1, and then multiply the vertical components. This should be a vertical components, v2 and w2, and then add them together. So we multiply the horizontal components, multiply the vertical components, and then add them together. And the dot product is always going to result in a scalar, because this number times this number is a scalar, this number times this number is a scalar. When we add the two scalars together, we get a scalar. So the dot product will not produce a new vector, it will produce a scalar. There is another form of vector multiplication called cross product that does produce a new vector, but we're not going to talk about that in here. All right, so example one, we have vector v dot w, dot vector w, for vector v is 3, 4, and w is 1, negative 2. So we multiply 3 times 1 and 4 times negative 2, and 3 times 1 is 3, plus negative 8 is negative 5. So we just get negative 5. And we're going to use dot product quite a bit to find angles between vectors and calculate projection and things like that. So if you're wondering where we're going to be using dot product, it'll be in a future video or two. So because the dot product produces a scalar, it's sometimes called the scalar product. So in other contexts, if you hear scalar product, it means the exact same thing as dot product. So it's tough in math because sometimes we have a bunch of different ways of saying the same thing. So as far as properties of the dot product, or properties of the scalar product, first up, the dot product is commutative. So v dot w and w dot v, it doesn't matter what order we go, we're going to get the same answer. So we can reverse the order for dot product and not change the result at all. We also have the distributive property where we have u dot and then in parentheses the sum of vector v and vector w. So it's u dot v plus u dot w. So it's almost like the distributive property for algebra. We have the scalar property where we have a scalar times vector v and then dot vector w. Well, we can take the dot product first and then multiply the dot product by the scalar, or we can move the scalar, instead of k times vector v, we could make it k times vector w and then take the dot product of that with vector v. And finally, we have vector v dot vector v. When you take a vector and dot product with itself, you get the square of the magnitude, and this is going to be central to starting our next example here in a moment. So when we take the dot product of a vector with itself, it's the magnitude squared. So in other words, it's the square root of x squared plus y squared, but then squared is just going to give you x squared plus y squared. All right, example 2 showed that the magnitude of v minus w squared is equal to the magnitude of v squared minus 2 times the dot product of v and w plus the magnitude of w squared. And we're going to see this with angles between vectors in a future video. So first up, we have vector v minus vector w squared. That's very similar to what we have here. So it's going to be vector v minus w dot product with itself. So vector v minus vector w, actually squared it should be, is vector v minus vector w dot vector v minus vector w. So this should actually be squared. So I apologize for that. Well, distributing our vectors here, using that distributive property, we have vector v dot vector v minus w, and then minus vector w dot vector v minus w. So it's almost like we distribute the vector v times this quantity and then negative vector w times this quantity as well. Well, when we distribute the vector v through, we get vector v dot vector v is vector v dot vector v minus vector v dot vector w, and then minus w dot vector v. Remember, it doesn't matter what order we go, so w dot v is the same as v dot w, and don't forget the negative out in front. And then negative times negative is positive, and vector w dot vector w is vector w dot vector w. Now here, vector v dot vector v, that's vector v squared, the magnitude of vector v squared. That's that last property we looked at in the previous slide. And then same thing here with vector w dot vector w. It's going to give us the magnitude of w squared. So negative vector v dot w minus vector v dot w is negative 2 vector v dot w. So these are just like terms like you would see in algebra class. Like negative x minus x would be negative 2x. And again, we have vector v dot vector v is the magnitude of v squared. Vector w dot vector w is the magnitude of w squared. And thus we've shown that vector v minus vector w squared, again, there should be a squared here, apologize for the typo, is equal to the magnitude of v squared minus 2 times the dot product of v and w plus the magnitude of w squared. And we will see this when we look at finding the angles between vectors as well. So thank you very much. I appreciate your time, and I'll see you later.